And in order to catch up and save time and hopefully go back to the original schedule, I'm going to introduce Bart Somers now to you. And I'm happy, Bart, I'm happy that you're here. Bart is from the Netherlands, and he lives in the eastern part of the Netherlands. And yeah, Bart got his ham radio license in 1996, and a few years ago, when cheap SDR receivers became available on the market, he switched from shortwave fun to learning SDR and GNUradio. And he loves to combine Raspberry Pis and SDRs and antennas and programming in Python, and all those funny things which we all like probably. And Bart is also quite an experienced Linux user, and he's working on that operating system since 1959. And Bart has the call sign Papa Echo 1 Romeo India Kilo, PE1 RIK, and he's going to talk to us on a field that's also very close to Inams, and this is why we scheduled his talk right behind Michael Hart's talk, because both topics deal about the spectrum and what's going on there. And Bart has been working on long-term spectrum monitoring together with GNUradio and Python. So as with the past talks also here, we're going to play in his pre-recorded video. And please, dear audience, do post your questions in the YouTube chat. And Bart will have enough time to respond to your questions already during the talk. And a little afterwards, if we see that there is something we need to respond with a video, but that's how we're going to proceed now. Okay, Sebastian, please go ahead with the pre-recorded video.
Hello, everybody. My name is Bart, Papa Echo 1, Romeo India Kilo, and I would like to share my journey into the spectrum monitoring using GNUradio I made last time. Let's start with a little background. Back in 2017, I gave some presentations on a Dutch RF seminar. I was just playing with the RTL SDR dongle, discovered RTL power, and was making spectrum plots using the famous heatmap.py tool from Mr. Keen. It gives you beautiful pictures, like this one. It's also a picture from 2017. And there are some interesting things in here. Over here, you see our local repeater. Every few minutes, it's just beeping out its call sign. Over here, the ISM band, also in our 70 centimeters band. And as one of our neighbors of our ham bands, you see the public mobile radio over here. It's all beautiful to see. But heat maps, they do have a problem. They give a beautiful insight on the spectrum usage, but there is no statistical information about the spectrum usage. You can't see any long-term information, and you definitely can't compare them to each other. The heat map I showed you was just 1 hour, but what happens 1 hour before, or 1 hour back, or 1 week before, or within a week? There's no easy way to compare them. So I want to make some statistical information and a better way to compare periods. And as I was really interested into GNUradio, I thought, let's try to make this into GNUradio. For statistic views of frequency usage, you have to do some requirements. You need a defined piece of spectrum with a single type of usage. If you have different type of usage into the same spectrum, it doesn't make sense to try to compare things on statistical information. For example, a broadcast FM station comparing with a narrow band repeater in one of our ham bands, it's 100% usage against, well, a few percentage. Remember one thing, the content of the information I'm monitoring is totally not important. I'm only looking for usage. So I'm not recording any content or whatever. I don't know who was transmitting, only there is a transmission. For this experiment, I choose the 2-meter repeater downlink band here in Europe. It's 200 kilohertz wide. It's only narrowband FM. If you take a DMR repeater, it's the same bandwidth. And I've got some repeaters available over here. So in this case, it's just 145.6 to 145.8 megahertz. Well, let's get to the details. The RF part. The antenna I use is the one that's on my roof over here. It's a Diamond V2000. And the SDR, I first started with the RTL SDR V3 dongle, which works fine in GNUradio. Later on, I shifted to my add-on Pluto, the Pluto SDR. But the Pluto SDR in its default situation doesn't support a 2-meter ham band. It starts somewhere up to from 300 megahertz. But if you apply the bootloader modification, it runs from approximately 70 megahertz up to 6 gigahertz. And it's a 12-bit SDR. You can definitely see it's more sensitive to small signal changes than the 8-bit RTL SDR. But one thing that's more important are filters. As a generic SDR is very wideband for receive, there's no filtering on the front end. And there's a broadcast FM transmitter very nearby. It's less than 200 meters away, and the antennas can see each other very clearly. So my RF front end is continuously overloaded. If I want, I can clearly listen to the broadcast FM somewhere up to 500 megahertz, and I don't apply any filters. So I applied an RTL SDR broadcast FM band stop filter. There are still some problems from digital television and digital radio transmitters, but it's much less already. The digital part, well, I want to run long term. So it means I have something which is on and which is 24/7 on for a prolonged period of time. And I choose the Raspberry Pi 3B. It does have enough performance for this. It's running GNUradio very fine. And it's power friendly. I have to tell you, you have to use cooling though. When it's getting hot, it's throttling. And you will see this happening into your throw gloves. But if you put in a fan and you have active cooling, it's running cool and it's running 100% performance all the time. GNUradio is 3.7. Why 3.7? It's default in Raspbian and on my Debian 10 desktop. I don't need to compile anything, and it works out of the box with the drivers from Pluto SDR. So well, maybe a little bit lazy, but it just works. And Python. Python for the tools, and Python for the embedded Python block I wrote. And GNUplot for the images. When you want to monitor 200 kilohertz of bandwidth, you need 200 samples per second and tune to the center frequency of 145.7 megahertz. But the Pluto SDR doesn't support native 200 kilosamples per second. The RTL SDR dongle doesn't neither, but they both support 2 megasamples per second. And by using a decimation factor of 10, you end up nicely at 200 samples per second. And the decimation factor of 10 is just throwing out 9 out of 10 samples. Integration. Well, it's interesting to see that you had 200,000 samples every second, which is a complex sample. But I'm not really interested in the entire content of the sample. I'm only interested in about the amplitude of the sample. So I apply a complex to magnitude squared calculation block to these samples, but then I still end up with 200,000 samples per second. I sum up 20,000 samples together. This is what we call integration, which ends up 10 values per second. So every 10 times a second, I've got an amplitude indication of the monitored spectrum band. Then I calculate a running average over these 10 samples. And the result is every second a smoothed power level indication of the band. But when there's an increasement in power level, I think it's usage, it definitely increases the value. And it's numerical, so you can really put a trigger on it. The flow graph, which was running here for a long period of time, is especially this. On the left-hand side, you see the Pluto SDR, and over here we have the DC blocker. DC blocker isn't necessary for every SDR, as a RTL SDR dongle in the driver can beautifully filter out the DC spike. The Pluto SDR does have a DC spike, so we need the small blocker over here. If you use another SDR, you might need to tune this DC blocker. the magnitude squared, calculation, integration, and moving average, as I told you before. And this was one of the learning curves into GNUradio. This is my own embedded Python block. You feed it a threshold, and when it rises the threshold, it gives a signal, and when it drops below the threshold, you get another signal. And that's basically the only thing what it does to the amplitude values from the flow graph, from the streams. Why would you ask, do you need a specific threshold? Can't you use a squelch for this? Well, a squelch triggers on an average power level in the monitored band. And this works well if the monitored band for the squelch equals to or is almost the same as the expected bandwidth. If you start monitoring a 12.5 kilohertz wide narrowband FM channel, some like 20 kilohertz, and there's a signal coming up, the average power level really increases in the small band. But if you have a small signal into a wide band, it doesn't work well. Within the 200 kilohertz, we get a small spike from a narrowband FM signal, and it definitely doesn't increase the average power level enough to trigger the squelch. So small signals really disappear when using a squelch. You can try lower your squelch, but sometimes your DC spike requires you to increase the squelch level, as the DC spike gives you a false positive on the squelch. In the description from the block, it clearly says it's an average power level. So this is the reason I took a threshold. I calculate the sum of all the power levels I have in the monitor band. And when a small signal appears in the band, it increases the total value, and it increases enough to place a trigger on it. The threshold printer. This is the famous block in here. You have to choose a value which presents an idle frequency usage beforehand. There are some tricks which I'll show you later on in this presentation. When the power increases, the value increases. The output which the block will print is like this for every opening or every time the threshold is triggered. It's above the threshold with, as you can see, the Unix timestamp, and under the threshold at the other timestamp. This was 2 seconds of higher power level in the monitor band. If you keep this running for exactly 1 hour, you have an overview of the openings in this band. And the second Python tool over in the toolbox, I can summarize this per hour. It's hour number 16, so it's on this specific day between 1600 and 1700 hours. It was 319 seconds above the threshold, which yields to 8.86% usage. The threshold was set to 0.9, and there were 141 times the threshold was triggered. Interesting, but what can we do with this information? First, let's see how we can define the threshold. There's also a GUI version of SpecMon, which is the tool I called it, where you can tune the parameters like gain, your frequency, and your threshold. It gives you a visual feedback. Over here you can see the options, and you see the screen isn't full screen because we can see the output box from GNUradio over here and see what's happening. The RF gain, the threshold, and the frequency. I also have a slider for the baseband gain in case you need in our SDR. Over here, there's a repeater nearby, which isn't very strong, but it was sending out its call sign. These are some other mixed products in the signal. And as you can see over here, it was the last line. You can see it was open for almost 5 seconds. And that was the time the repeater was sending out its call sign. The bar over here gives you the current value of the amplitude. So you can see, well, with a threshold value of 0.25, it really works well. And it can start moving around a little bit in some noise without triggering the threshold. Searching the right value for your threshold can be a little bit cumbersome, but that's depending on the noise levels and the signal levels in your area. Well, If you keep this running for hours, an entire day, and more than days, you've got three types of data per day. The percentage of usage over the day, seconds in the hour. You got the number of openings, and you got the average time of openings in seconds. And you can visualize these. This is an example. We're looking to May 6th, and as you can see over here, it's approximately 33% usage of the band. It's 33% of the usage of the 200 kilohertz I'm monitoring. Between 9 and 10, and between 10 and 11, it dropped a little bit. If we see the average time of openings, it's approximately 110 seconds. This was activity on the repeaters, which is logically because when the repeater is open and someone else continues the QSO, the repeater remains open. So the time can come up quickly. Down here, we can see the number of openings, which doesn't increase very much over here, which is quite logical too, because when the repeater is open, it remains open. So there are not much further increasements. There is a baseline around 6 over here in the entire flow graph, or in the entire graph. And that's we can explain this by every 10 minutes, the repeater is sending out their call signs. So there always will be 6 openings into the hour during the entire day. If you start running this for weeks, you can see some other patterns coming up. This is May 5th. May 5th is a national holiday. The graph looks a little bit the same, but unless we were talking 33%, this is just 9%. And it's just 19 average opening times in seconds. So there were just some openings additionally on the repeater. And still the baseline remains approximately around 6. If you start combining weeks of logs, you can start to see interesting patterns over in the time. When you show the percentage per hour per day and combine this to the logging of 1 week, you can see the entire pattern over the week. And you can integrate the usage per day and then combine the logging to a single week with a single number for every day. Let me give you an example. This is April 26, and this is interesting. We've got April 31, April 32, and April 33, which is actually May 1st, 2nd, and 3rd. But for the graph, it was nicer to number it 31, 32, and 33. If we take a look over here, which is May 2nd, but it's also a Saturday, there's hardly any usage. The other thing, which you can see, is April 27. It's a Monday. We're in the morning, there's hardly any usage. April 27 is King's Day, which is a national holiday in the Netherlands. In the other days, there is some usage. And on Sunday, we've got our weekly meetups, I guess, on the repeaters, and there's quite a lot of activity. The next week. Again, we've got the Monday over here. It's not a national holiday. So there's just activity in the morning. But May the 5th was a national holiday. So there's no activity. Again, on Sunday, there's activity. On Saturday, hardly any. And on Friday, I guess everybody was off. The weather was beautiful. And on Saturday, doing the shoppings. This is a pattern I can see clearly in several weeks. This week is not a holiday. The former 2 weeks were school holidays over here. Again, over here on Saturday, we are hardly using the repeaters, doing some shoppings, but that was basically all the activities. And the patterns over here remain the same. In the evening, we got some activity. And on Wednesday evening, there's also a meetup. And on Sunday, May the 17th was very beautiful weather. and there were a lot of people outside enjoying the weather, so there was some less activity on the repeater. You can even start comparing individual days. Because we've got information from all the days, we can start picking the same day in the week, but over different weeks. So what I did is I took these 4 days, and they're all Thursdays: April 30, May 7, May 14th, and May 21. May 21 is Ascension Day. Can we spot this? Well, yes. There's no activity in the evening. We were all off, enjoying family life, having contact. I don't know, but there was no activity. Thursday in the morning, there is a default period of time with activity. And in the evening, also, I think somewhere between 8 and 10, we are upstairs using our radios and having some activities, except the holiday. Well, we can even integrate some daily loggings. So look, what are the statistics of usage per day? Over the entire day, not per hour, but just over the 24 hours from the entire day. And this is the week I'm going to plot, because there are still the same weeks, and the first and the second week are normal holiday weeks. This is just a combining of all the information from the log files from the hours, and then combining them to this a single percentage of the day. And as you can see, the Fridays and the Saturdays, we are not really using our ham bands, in this case the 2-meter ham band, that much. Thursday, there's more usage, and in the weekend, we use our repeaters quite a lot of more. And if we plot this, we can see the numbers I showed you before into the graph. And again, in the weekend, it's increasing. Friday and Saturday are still quiet days on our repeaters. If you need activity, you better search for other days. There are some other things I learned during these experiments. The Pluto SDR is a beautiful SDR platform, but it does have some issues. And occasionally I've got some USB connection problems. Sometimes during measurements, and incidentally I had to unplug and replug the USB again. And it happens approximately once a week. I couldn't find any cause for it. Sometimes there was just 1 hour without any measurements, and then the next hour it was running. Maybe all the repeaters were dead, not so logically. But there's another problem, and that's clock stability. According to the manufacturer, it has a stability of plus of 20 minus 25 ppms. So that's a possible drift on the 2-meter band of 3.6 kilohertz. Well, it's shifting around a little bit, but we're not losing really entire NBFM channels. But on 70 centimeters, it can shift up to 10 kilohertz using the 25 ppm. So you even can start losing an entire channel while shifting in and out of the band. Don't think about what would happen on 23 centimeters band or even up. So with this setup, it is possible to generate usage statistics and compare the several data sets over several days, which isn't really possible using the heat maps I showed you before. The gathered data, on the other hand, is not fully reliable. There are 2 simultaneous transmissions are counted as one. I got 2 other repeaters, the one I showed you before in the neighborhood, and they start sending out their call signs every 10 minutes. But they are time synchronized. And if you look into the spectrum, they open up at exactly the same time, and the call sign is almost the same length, so they drop off almost at the same time. There's one increasement in power level of the band, but these are actually 2 transmissions. Changing the background noise also can probably cause false positives. I haven't monitored every single hour in this measurement, but I think somewhere in during the day there are some increasements in noise, background noise, RFI, haven't figured it out, which probably triggered the threshold and put some measurements in there which shouldn't be there. And there are some things I would like to improve in the future. The dynamic threshold, as I told you before. If the background noise is changing, maybe we need to change the threshold over the day. Due to all the integrations and averaging, I have a time slot of 1 second. If I want to decrease the time slot, maybe it's possible to see bursts. If you got a very small burst right now, due to all the integrations, it wouldn't show you the increasement of power level. So we need to tweak around and make some short bursts visible. I need a stable clock for UHF and up. Modify my Pluto, use another SDR. I have to think about it. But thinking about these things, there are some other questions. Can we see propagation change? If the noise is changing, or maybe there's some even more activity. If we monitor the beacon band, can we see propagation changes? There was a problem with the multiple repeaters beeping at the same time, being one transmission where they actually should be two. Is there a possibility to monitor on channel usage, so channelize the information? And one thing I would like to experiment with, combination with the burst, is can we, for example, see radar reflections from the Graves radar in France over here? It should be doable, but not when I integrate everything to a single second. So we have to tune about it. So these are things I learned, and I still have some questions. One of the things I learned is GNUradio is a beautiful tool, and I'm able to write in my own embedded Python block to do some things. I hope you enjoyed this presentation and would like to thank you for your attention. The software you can find on my GitHub page is over here, and you can send me an email if you have further questions. Thank you.
So here in our studio room, and we've already been discussing questions and responding to questions in the chat. And so I think, Bart, do you still want to respond to any particular question live? Or is everything okay?
If there's still time for it, else I can take the questions in the chat.
Okay, very quickly. Is that possible?
Yeah.
Okay. People saying thank you.
Well, thank you for all the interesting feedback.
Oh, Ivaris is also here. I see him here in the chat. Well, okay. So I see it's okay when we're responding in a written form in the chat function of the YouTube channel. Bart, thank you very, very much for giving this interesting talk to us. Let's clap hands.
Thank you very much.
Let's applaud the great public. You can't hear them applauding, but I'm sure they will also applaud at home or wherever they are. Thanks very, very much again. That was a very interesting insight. And well, if there are any more questions, please, dear audience, do submit your questions in the chat, and Bart will be responding to them.
Well, thank you for the platform and the possibility to give my presentation, and I will be in the chat.
Okay, thank you very much. So we're going to change studios very smoothly and go over to the other studio room of our conference server. So Bart, thank you very much, and hope to see you next year again, maybe in Friedrichshafen when we're there again, or otherwise, I think we're also going to have at least an online option for the next conferences, so maybe also again via a teleconference. We'll see that. Thank you very much.
Thank you very much, Bart.
Thank you.